We ended here with the augmentation in the previous part. And this is a way to grow your data set if you don't have enough data. And it's often the case that you couldn't get maybe more than a few data sets, but you can still give the algorithms a chance to get more variations, and that is through the augmentation. And okay, I just need to move over here. So now it should work. So, and the types of augmentation you can do on the data are transformations. You can do shifts, so you just translate in different way. Zoom, scaling, rotation of the objects. Can also change in the intensity, and normalization is also kind of a intensity, but could also be shape normalization. Scaling is kind of similar to zoom, and you can also play with the color ranges, and shear can also be a possibility that you pull it in different corners and shear the images so they get a little bit stretched diagonally. In adding to that, you can also do add noise with different signal to noise ratio. You can also add blurring to the data, and if you batch everything together, you have quite much greater variation in the data set. And here's an example. This is retina scan, and it shows some of these variations. So you have the original data with its ground truth, then doing some elastic modification of data according to some random wavy grid pattern. And you can rotate it. In this case, it was rotated 30 degrees. You can also do some zooming on the data, and then you can see the effect, how the data changes with that. And that gives more variations, and it helps you also to improve your data set and the training variations. This was prepared by a master student of mine some years ago, and the data came from the Drive database. So that's a database. Yes?
It's a quick question. If we do this kind of augmentation, do we make, or can we create our algorithm more robust to these kind of transformations?
Yes, yes.
So if we look at medical images or cars or places,
Mm-hmm.
we cannot make up variability, right?
Yes, so yeah, that's I think I come to that soon. There are limits for how much you can do it. It is not, so you have to do it in the limits of what is naturally expected. For example, rotations can often be quite freely done, translations as well, but scaling, for example, if you have humans, they cannot be 3 meters tall. So that's, say, the limitation that you have to put into this augmentation. Also elastic, if all of a sudden you have one eye here and one eye here, it doesn't really make sense. So that you have to tune in and see what does it mean if I do the extremes. So that is something you have to put into the augmentation task. But you can still add also the noise factor, different colorings. If it's pictures of people or cars, you can also look into the light intensity. Could be dark, could be brighter. So that kind of variations you can always do. Also, if it's humans, you can probably not say they are green, mostly not. So that would also be one kind of restriction on the color scale. So this is actually the limitations that you were asking about. So, for example, CT images should normally not be flipped. So you cannot take and flip the skull upside down. It should have orientations given. That is usually given already in the DICOM data if you have CT scan data. That orientations are already given. This is up and this is down, and if you start rotating things in that coordinate system, you kind of get lost. So that is important to keep track of. And also the intensity values. I gave the example before, you can have daylight, nighttime. That would make it possible to change the ranges, but if you look at, say, CT images, the CT values actually have a physical meaning, and they shouldn't be varying too much. Otherwise, it doesn't make physically sense in what it's representing, because the attenuation coefficients of the X-rays gives a certain range for different tissue. So there you can't change it so much. And then, of course, how much distortion is allowed. The extreme case is, can you still recognize the features? In some cases, you can distort it beyond recognition, then it doesn't also make much sense. And yeah. And to do this, there is this little machine called the Keras data generator. It's a lot of text here, but in principle, what it allows is actually in a single line, you can actually apply all these variations. You can give it each kind of change a boundary. You can switch on and off different possibilities. And if you would just look at the help for this data generator, you can see more details about what you can do. So here is one example where different things are switched off, and then we have actually I don't know what ZCA is. Then you have rotation. That means you can rotate in the range of 30 degrees. Also shifting, how much you can shift the images, and it's in this case it's not allowed to flip vertically or horizontally. Maybe it would be for some X-ray data. If you start flipping things, you may have an unnatural behavior in the data. So you really have to set the range when you generate the data in this way. And this one I need to execute. And this is just the configuration, and then afterwards you use it in some code. So here it's a lot of code, but the important thing is we load the data from TensorFlow datasets, convert it into NumPy, and load the dataset. And here we just we say the MNIST data, take the test dataset. We have only one batch, and as supervised, there's another parameter telling how the training is taking place. And what we use here is this IMG aug. That was the augmentator that we initiated, and we tell it to work with the first 10 images and 10 labels, and we don't shuffle it. So there is no random permutation of the data. The rest is extracting these augmentations that we get here with the next, and then you get the image batch and the label batch, and then there's a lot of plotting. So in principle, what you need is first setting up the augmenter, load the data, and okay, you need to do some fitting here so that it knows what data it should work with, and then we start the flowing, and finally extracting the sets. So these are the steps you need to work with. And okay, yeah, so this is another data set that we can work with. It's also a classic one. The CFAR is our, let's see, so that's better. It's also a large data set with very many variations. You have airplanes, cars, birds, etc., etc. And it's popular to use. And this is what we're going to load in an example. So here we take the data set. In this case, we take the CFAR and load. And then we run the data generator with a lot of parameters, a lot of shifting and shearing and rotations and so on. Fill mode is an interesting one. It's when you have doing all these rotations, then there will be a gap, rotations and translations, scalings, there will be a gap which is not filled with data. And what it's doing then is just filling up with reflecting the previous, and then it's filling in with the reflection in the missing area. So for example, let's, a clean one. So if you would have original image like this, then it's rotated and it comes like this, and the image would turn out in this area. Then you would take this, let's see, this piece here and flip it over here. That would be the reflection. Just to not having black corners, yes.
Does it mean you miss data then?
It is kind of filling in missing data, yes.
But you're also erasing data, right? Because everything which is now not...
Yes, yes, yes. It's kind of the cost that you, when you start changing the size or positions, there is some data loss. In some cases, it could also be roll around. That could be that you have the image, it's moved in this direction. Then you have some piece is going out here, and then you just put it back on the other side. It's a question what you should do, because this is kind of special cases in what comes out. And that the edge problem is ever returning, and that's why it's sometimes, I don't think it's here, no. Sometimes when you do filtering, you can choose between some kind of reflection or only using the valid area, the one that you know that it's, and then you actually reduce the size. So if you would take the valid area, all of a sudden when you do the rotation, you would only use maybe something like this instead. But then you have smaller images, which is maybe not what you want. Yeah, and then we have this augmenter. I think I need to run that one, otherwise it will not happen. So, and running this augmenter, then we will see what comes out. There we have some images, and I think I need to go out of display mode. And now you can see what happens. Seems to be a quite extreme. Here you see the example of the flipping, what happens on the horse here. It's rotated, and you can see that it's doing mirrors. You get a flip here, you get also here. You can see the legs is coming back again. And that's why you always need to look at the data you augment to be sure that it's actually the thing that you want to detect, because this one doesn't look like a horse anymore. If you would say, look at that image, I wouldn't say it is a horse. So, and also that one is pretty hard to tell, is that really a horse? So it's quite stretched, so it's just a fraction of a horse. And so you really need to, if you do this augmentation, you should plot this kind of overview of what it does, just to get a visual feedback. Is it really that what you want? Yeah, so much about that. Now switching over to baselines. And a baseline is not data, but it's actually a first type of algorithm that you use. And typically, a baseline is very simple and shouldn't take too long time to implement. It should do something that at least approaches the solution to a problem. Doesn't have to be fantastic good, and it's kind of a worst case scenario of how it can be performed. And there could be even use cases of it that is completely useless. And why we need this is to have something to benchmark our real development with. So let's say we have a baseline model which says that 99%, more than 99% accurate for breast cancer. And an algorithm that would do that is that we say, do I have breast cancer? No. That would actually be a true answer in more than 99% of the cases, because it's apparently 0.09% of the women would have breast cancer. So this would be good generally, but in the end, it wouldn't actually target the problem that we are looking at. But it's a benchmark, a baseline model. And we should be better than this. And this is also a case of data imbalance. So if there is only 89 out of 100,000, it's not very easy to spot it. And for that, there are a couple of available classifiers that we can work with. So in scikit-learn, that's a package that we can import and use. Very good starting point to go to scikit-learn, because there's a lot of nice algorithms in it. One of them is the dummy classifier. And one approach for baseline would be to do most frequent. So it essentially just counts how many there are of each. And the class that is most frequently occurring is the one that will give the answer. So if we have this use case where we have 3 observations, 1, 2, 3, and we say that we have one healthy cancer, and let's train that one, and yeah, it needs to load it first. So then we got our classifier, and going on and trying to predict using this classifier. We can see here we trained this DC, and then we just use the predict. So we look at these data that we had, and no, actually IDX is here from this loop. So we have the observations 0, 1, and 3, and 100. And what is the result? We say that all are healthy, even though a 3 should be cancer. But as we have the most frequent, it says that everybody are healthy. 100 wasn't in the training data set, but it extrapolates still that if it's not in the set, it's still healthy. Then we can try this dummy classifier on the MNIST number data set. And let's see, yeah, we just load the data and show it, and a histogram. So here we have the numbers. You can see the distribution of the numbers. They're not, the axis here is not so good, but anyway, you can see we have the different numbers. You can see that we have 0s, 1s, 2s, etc., etc. And now we train this dummy classifier for that. We again have the most frequent, and we fit on all the images we loaded, and that turns out pretty good. So we have our classifier trained, and then we take the first 10 images and try to do a prediction on them. And the prediction says all are ones. But as you may have seen here, we don't have all ones. So what is the dummy classifier doing? An idea? Yeah?
Taking the most frequent, it was
Yes.
the most ones in the picture.
Yes, exactly. So that is what's happening. And let's try it on the images, plot them out, and see what happens. So here we can see that Mostly it's actually doing a misprediction, and when it gets a 1, it's actually doing the right thing, but it's not really. That's more or less just by pure chance that it gets there. So, the answer comes already. You answered it already right. So let's looking at the histogram. We can see in the histogram that the 1s, they're actually the most frequent, and that is what it's trained for. Another baseline that we can use is nearest neighbor, and that's an algorithm that I'm going to talk about in more detail and explore in more detail in, I think, lecture 5 or 6, 5, I think. The idea is that if you have a data point in a scattered cloud, first you train, and you say that each data point has an assignment. In this case, we have a 2-dimensional decision space where we have measurement 1 and measurement 2. It gives us this distribution. And the idea of nearest neighbor is that if you have a point which is maybe here, it looks in the compares with all the neighbors, and the one that is closest is telling which class it is, which class this observation belongs to. So this is the case when you have just a single neighbor, and then you can increase, and in this more complicated plot here, you compare to 9 neighbors, so you take the majority out of 9 neighbors. That's pretty good starting point also to compare with. And as you can see, it's not a linear decision space, so you can really get pretty complicated shapes here, decision spaces. But I'm going to talk more about that in a few lectures. And let's load the data again and see what we can do with it. We have the numbers as we had them before. And now we can see what it does. Let's see, this was executed. We got them. And now we are getting, again from scikit-learn, getting neighbors, k-neighbors classifier. And we are playing here with 1 neighbor, and we try to fit that into the data. We'll probably run a little bit. Yep. And now we want to do prediction on our images again and see what comes out. And this time we're getting a mix of numbers. Maybe it's right, maybe it's not. That we have to see on the next slide. And now the outcome. Wow, fantastic. Yeah.
What are the features in this case?
The features is just the number, the gray level. So it's kind of comparing to. No, wait. In this case, yeah, it must be the gray level, I think. So the average area or something. But the problem here now, so this is too good. I mean, if we would have that, we would be happy. But what can you imagine what the problem is here? Giving the hint that it's nearest neighbor.
The training data is the same as the testing.
Exactly. So what would happen? So the problem is when we have the nearest neighbor and you're testing exactly the same dot against each other, then they are always the nearest neighbor. So that is what's happening. And if we would run it with a different data set, then we can see that it's not always doing the right thing. So then all of a sudden, sometimes we're doing right, sometimes we're not doing right. And this measurement is then based on the white pixels or the pixel intensity. And here now you see when we change the data set, I would guess we have something like 50%. So it's more or less a random guess in that case. Because the input information that we are working with is not sufficiently quantifying what we actually see. A way to look at how good this segmentation is to use a confusion matrix, and it's built up with these elements that we have or in the binary case, we have 4 elements. We have actual true versus predicted true, actual false versus predicted true and predicted false, and then the actual true also against the predicted false. So what we want in the confusion matrix is that we have a diagonal where all numbers are, and in this other diagonal should be 0 ideally, but we don't have that because our segmentation is not always so good. And we can look at the confusion matrix for the MNIST classification using these. No, come on. So that one I want to look at fully. So it's a bit dark now, but you can see that it's first of all the accuracy is 56.9%, and you can see that mostly it's doing pretty good, but there are cases when you can, very dark here now, where you can see that some numbers, they are mispredicted, and there are some cases that are very confusing. For example, here, the 4 versus the 9, it's almost the same. 1 should shine up with a 7 at least, pretty well. And that gives us an idea which are the tricky places. And then when we start doing our own development, we can look at, for example, the confusion matrix to see how does it perform versus the baseline algorithm. So what we want is more or less that more and more are focused in the central region here, along the main diagonal. So, the last part for today is about data frames. This is a tool that is used a lot to handle data in different analysis. So we have a lot of the workflow is that we need to have some image analysis, then we extract and select different features, and finally want to present the data. And typically, we have here some input data, which is processed, doing some Python scripting or something else. And this result could be stored either in the cloud somewhere, if you have a big data set, or could even be saved in some kind of spreadsheet. And finally, you want this result to be plotted in some plot with that tells the story you want to tell with the data. And the data frames should be stored, can be used to store our data. So we have different ways to store data. One is using arrays or dictionaries, some kind of structures, but it's not very flexible, and can also be difficult to do. Then you have to write a lot of code to do counting or some statistics or selecting sub-pieces of the data. And that is a bit problematic because it takes time to do all this extraction, and the flexibility is limited. And the risk when you start writing everything yourself is that you can also make a lot of errors, and you have to make sure that this code also does what it's supposed to. Here, the data frames come to help, and the data frame could in principle be compared with some kind of coded spreadsheet. It's a data container, so you have rows with the entries, and you have columns for the categories, and it takes any data in the columns, which means you can have images, you can have just scalars, you can have strings, whatever you want to have there, and then you can do interesting operations on it. For example, we can apply different filters for selecting subsets of the data. So say you want select all observations that are within some range of, say, ages. So you want 10 to 20 years. And then it will give you a subset of the data frame quite easily. So it's including, it's not only a spreadsheet, but it's also kind of a database. So you can do queries on the data. Then you can also do sorting if you want. You can perform arithmetics, compute statistics, and what is not mentioned here, you can also directly do plots from these data frames. And of course, when you have produced some data, it's also important that you can load and save the data somewhere. There is a big documentation available at Pandas. So the data frame we are going to use now is the Pandas data frame. There are other alternatives if your data is getting huge. Maybe it's even distributed. Then you can use other data frames, but many of them have more or less the same syntax as the Pandas data frame, so it's easy to make a step over to those. So to do it, there are different ways. So the first step is we create, first we need to import this Pandas data frames. Typically, it's import Pandas as PD. PD is the abbreviation that has turned into a standard, actually. And the good thing here is that if you would replace this Pandas with some other data frame with the same syntax, you don't have to rewrite your whole code. It's just you change the data frame package and then continue using just PD, and it behaves the same way. So it's pretty convenient, actually. The way you can create your data frame is from a dictionary, from a data file, or from NumPy arrays. And did I execute it? No, I didn't. Let's do. And first is loading from a spreadsheet. We can just do PD read CSV, which stands for comma-separated values. And then there is this table. And if we execute this, we load it and show a selection of 5 rows from this data set. So it's a phenotype table from, I think it was some X-ray experiment on bones. And the exact numbers we don't care about right now, but you can see that you can load this kind of data set, and this sample is making a random selection somewhere in the data frame. So you can see the numbers here. This is the index of each row. You can see they are also scrambled, so it's not even sorted here. But it's just to get an overview of the data, what it looks like when you have loaded it. And saving works in a similar way. So we can just go here and do our data frame, which we call pheno, to CSV. There are also other data formats. I think you can also do to Excel if you like directly, then it lands in some Excel spreadsheet. But CSV is pure text and can also be imported easily in Excel if you like. So then you can just save that one, and then we have a new copy of the data. Could be that, for example, you make some selection or maybe extra calculations on the data, and these you can then save after you have processed it. Another way to work with the data frames is using dictionaries, and that's a kind of a lookup table where you have a label and some value connected with it. So in this case, I'm creating a dictionary with, actually it's a a list of small dictionaries. So we have position, which is given the value I, and then you have a value, which is given a sign of this I. And if I execute that, you can see what it looks like. It's just a list of values and sign values and positions, and each is labeled. And to create a data frame from that is just bringing this dictionary in. So you do PD data frame and take your dictionary, and there you can plot a sample out of it. And then it comes out, instead of this not so easily readable, the data frame, when you print it, comes out in a nice formatted table form, which is easy to look at. And yeah, this was still randomized. We could, in principle, also the dictionary is ordered, and if you want, so you looking at a sample is meaning it's taking a random selection. No, so if you want the first 5, then you write here head 5, and then you get them ordered in the way they appeared in the entry. Yes.
Does this only work if you have a list of dictionaries, or if you just
No.
put a dictionary?
You can reverse it, so you can have also, I come to that. So instead you can have a dictionary with only a category and a list inside. Category, next list. That's also possible. Pandas understands both cases. So it's, yes, let's switch on to the next one. Yeah, exactly, your question. Here, instead, we create a dictionary with only 2 entries. And it turns out pretty much the same. Here I did some scaling also. So here I created a linspace. That means I created an array with 100 elements in the interval 0 to 2 pi. And then I compute the sign values, and then I create this little dictionary where I put in the positions. It's the whole long list, or actually it's a NumPy array. And the sign gets another list, and that can also be added. And then you see here, you have, again, positions and nice tabulated. So, next thing is working with columns. And now we want to add, we have this data frame and we want to add a new column. For example, you want to compute the cosine, because it's not enough to have the sign only. Then we can just easily add this data frame cosine. So it's adding a new column which is not existing, and we give it a value. Then it's automatically added. So you don't have to do any add column function. It's just saying when you provide a new name, it takes it as a new column. And what we do is we take the cosine of the position column and computes that. Then we can also do a sum column where we look at that. We take the sum of sine and cosine, and we can even do a first test. We check if it's positive, and looking at the outcome of that, we get, now we see that the original table has now been updated, so we have 3 more columns. So we have the cosine, we have the sum of sine and cosine, and then we can see if the sign is positive or negative in these. Oh, actually greater than 0. So it's, this one is false, and then when we see the negative one, it also says it's false. So you can, yeah, you had a question? Yeah.
The DF columns are arrays, or they are specific pandas data type?
Pardon? It's
The columns.
yeah.
Because how can we put them directly on the NumPy cosine function?
The output of a column is a NumPy array. So it's a mix between NumPy and data frame. So you can apply this in the very detailed end. It's essentially just a list, and that is what it's operating on. So yeah, you can apply all the NumPy information. And switch on. And now I said before that you can do some filtering. So now I want to create a new data frame where I select only those rows where the sign is greater than 0. So here we can just execute this. So what I'm doing is I'm indexing the table with this criterion. So wherever the column sign is greater than 0, it will be added to the new data frame too. And looking at it, oops, we can see here that the data frame we have is only full of positive sign values, and we can also see here that it's positive. We could also just take the positive column and say that is our indexer. So the indexing, when you do filtering, is in principle a Boolean, so it's either true or false. So if I would take here instead, just as a test, and let's do a df3 equal to df2, df, and df positive. What you saw I did now, you saw I had this little list, is that you can always press tab to get the completion or suggestions for completion. So this should, in principle, turn out the same way as df3 head 5. Should turn out the same way. Oh, that's annoying. Okay, I need to do another line. Now it's only showing the output of the last one. That's the problem. The positive here, I'm using this column, so I can use a Boolean column as indexer. But now it only shows one because it always shows only the last. That's a bit stupid, actually. Yeah, so. And there it came. Okay. Then we can also rename. So for example, if you load data from this CSV example, maybe you don't like the naming they use there, then you can rename it. And let's say you created here a little table where you have the columns are named A and B, and you don't want that. Then you can use this rename function where you say that the column A is renamed into hay and column B is renamed to hop. So then you can just execute that and you see that A and B have been replaced. So that's kind of a decoration thing. Sometimes it's a matter of convenience that you want to rename it. Maybe the names were too long or not explaining what you wanted. So then you can just do renaming. Then you can do statistics also based on the data frames. So you can compute the mean of the data frame, for example. And then it computes the mean of every column. And that may not be relevant, so you can also use indexing, specifying which column you want to compute the statistics on. Another option is to use describe, and that's doing a lot of calculations for you directly. So instead of writing df mean, df std, and so on, then this describe actually gives you a lot of information in a single command. So you get already the count, how many, the mean, standard deviation, minimum value, 25%, quantile, 50, 75, and the maximum value. So this you get in a single command, so you can get a quick overview of the data. And yeah, then you can do a lot of mess with filtering, saying you want to look at, let's see, when, what is it now? Okay, in this case, you want to look at the average standard deviation of the sine column in the case when the sum of sinus and cosinus is greater than 0, and then you can get that value. So you can really mess up these queries quite a lot, and then you can select just a single column, and this would be just a single scalar. And let's skip this grouping. It's just, I'm not going to explain this. It's a bit messy right now, but you can look at the example afterwards. But in principle, when you do this description, you can do grouping, and you can get a different presentation, and you can reduce the table into something more comprehensible in the end. Like you have the mean values and the variances for true and false. You can really boil it down to that. And as I'm in a little bit of time pressure now, so plotting can be done in the same way. So you already last time, I think you saw a bit of plotting. You can also plot the data frame content by just saying df.plot, and you tell which plotting axis you want to use. And the outcome would be this, that where you can see that the position is just a linear increasing, and then you have the different signs here. And that can be also selected, so you can do just plotting the sine curve, or you can even plot, select which axis which column should be plotted at. And here you can see the outcome of that. You see this, just the sine. Here is sine versus cosine, and then you got naturally a circle. And you can even do some function plotting. So as again, it's just a function of position. Then you get the axis correctly labeled, which we don't see now because it's outside. Come on, so yeah, see. Yeah, but it's anyway just numbers 0 to 10, so it's you don't see it really here. Okay. Yeah, the last part here we skip and go on to. Yeah, we conclude here. So you can look at there are some more complicated, more set operations between different columns, how you can merge them if you have two data frames, but I think I skipped that for today. Leave it for your own reading, and also take a look, if you want to use pandas data frames, look at the documentation. It's well written, and it gives you most of the information you would need here. Just the last slide is when we can use these data frames, and that depends a little bit on the data size. If you use it for raw images, it depends on the size of the images. Can you actually put all your data in your RAM? Because the pandas data frames, they are in the computer, need to be loaded in the RAM of the computer. So there is a limitation there. And then with the segmented images, then you already have just black and white, take less space, so then it's more realistic. Feature data, certainly, because it's just strings or numbers. Statistics, well, that's certainly also. And when you go to modeling, you can actually make a table of model values, for example, and then, of course, you can also use it. If you want to use big data sets, then you can go for example, Dask data frames, which can be distributed on, and it only loads what you need for the moment. So that is the option to look at in that case. Yeah, and that was all for today. There's a little summary. Sorry. Next week We are going to look into noise in images and filters to enhance different parts of the image. And yeah, that would be the end of today. Let's see. That's it.